So we talked about the parallel algorithms using Java. We demonstrate some of the key capabilities, and now what we will do is we will look into other software related or programming related parallel and distributed models. So the next architecture that we will be discussing is the distributed memory or message passing model. So this mainly involved in large applications where one single machine is not capable enough of handling everything within the application. So when we are running when we are running applications, most of the time the hardware capabilities always strict us by using massively parallel algorithms. So the main reason is we have defined amount of memory, we have defined amount of a hard disk and resources that we can plug into a certain machine. Okay, that means only the machine which is running the algorithms, they have limitations, mostly hardware limitations. So to achieve a huge to run a huge parallel algorithms, sometimes the hardware capabilities of one single machine won't be enough. So what we do is as we have discussed earlier on, there are algorithms where we can send out the parallel things into two or more than different machines, so they can communicate with each other and get the things done. Okay, so what we do in here is this message passing or message passing model, or distributed memory model we call it, that a task can be run within more than one or two machines. So to communicate with each other, to send the data, to work with the ongoing algorithm, so they will be using message passing mechanism to send out the data which is needed to work with the parallel algorithm. So this is kind of the basic way of doing in distributed memory message passing models. So let's see what are the characteristics and what are the implementation available right now. So these are the following characteristics that we will see. A set of tasks that use their own local memory during computation. Multiple tasks can reside in the same physical machine and can access arbitrary number of machines. So one single task is running on one single machine, and within that single machine, there can be multiple tasks. Okay, so as you can see within the diagram, machine A is running a task 0 and machine B is running task 1 and 3. So machine A, which runs task 0, will distribute some of its works, will send some work to machine B, or they can communicate with each other, maybe in different contexts of the task. So we have one task running on task machine A, and we have a completely different task which rely on the task 0 is running on compute machine B over here. So once the task A is done, or it's halfway there, it can send its data to the machine B to continue the work, or to completely hand over the task which is running right now in machine B. So everything that's happening in machine A can be transferred to machine B. And the same goes with the another task. So as you can see, machine A can have multiple tasks. They can communicate vice versa. Machine B also can send some data which is computed by machine B. So the sending data across physical machines should happen within a boundary of network. Okay, so we can have a physical network, like when we are using LAN or WAN, whatever the network, as long as they are interconnected, we can communicate. It's not it's not like mandatory to run this in the local environment, local machine. They can be apart geographically. That doesn't matter, as long as they are connected with each other. We can continue this. We can continue the data sharing. So over the internet is also possible, but the question rise, if we have a large amount of data to be transferred, the network latencies, network delays, those kind of things will not work as expected. So in order to make sure that these things work without an issue, the network should be very strong. It should not have any lags. It should be accessible, and the bandwidth capabilities. We should always think about those things when we are working with this kind of models. Tasks exchange data through communicating by sending and receiving messages. Okay, so whenever we want to communicate, so let's say, for example, task A want to do a subtask on this. Okay, that subtask is task 1. So what task 0 want to do is need to provide all the information, all the data that need to be processed by machine B. So a simple message sending algorithm, there are a lot of out there in the modern world. We can send, think of as we are sending an SMS from one machine, one phone to another. So we are feeding information from one end to the other. So the receiving end, okay, says, all right, we got this message and we will act accordingly. So these messages is sent via the network. Also, you guys can see that it's a two-directional communication. That means either one of these machines can send or receive messages. So based on the message they are going to be receiving, they will act upon it. So the next point that we need to think about is the data transfers usually requires a cooperative operation to be performed by each operation. For example, sending operation must have a matching receiving operation. Yeah. So these two mechanisms should have a cooperating operations. That means once we send the message, the receiving party should accept that kind of messages. So if you are not accepting these messages when we are sending these things, then there's going to be a little bit of a situation where we are sending the message, but there are no receivers to accept that message. Then who is responsible for handling that kind of data? So we need to make sure whoever we are sending these messages from machine A to machine B, it's going to be a cooperative collaboration. So one party send a message, the other party is receiving, and the receiving party should know how to process. The sending party should know where to send. Okay, you can't send a location where you don't know or where you are sending wrong information. The information should always send for the intended party or intended endpoint. So this is something like more of a server client architecture or server to server architecture, server to server communication. So actually, basically in server client architecture, we normally have a client is requesting something from the server, but there are bidirectional communication where server can also send. But theoretically, in machine-to-machine communication, in this scenario, either party should be able to send a request, and the receiving party should cope with that request. So implementation, from programming perspective, massive parallel implementation usually compromises libraries subroutines. Calls these subroutines is embedded into source code. The programming responsibility to determine all parallel subs. So when we are working with message passing, and especially in context of parallel computing, we need to make sure the programmer knows, okay, when we are executing the parallel algorithms, we are sending some chunk of data to another machine, and that machine will accept that and work on the things that we have said. So that's kind of things when we are working in the application. The source code is responsible for, okay, I have, let's say, 10 instructions with 10 data that I need to send over to another machine and get it processed. So the source code should handle, okay, these set of instructions will be handed over to another machine, and that machine will respond back with the data. So in a way, the source code management, the people who are behind these parallel algorithm design, they should be able to send this data and receive the messages back on. So message sending, there are a lot of ways out there that we can do. That we can do in order to do parallelism. Okay, so there should be a standard way of communicating. Otherwise, the machines, the algorithms, the programming models that we're going to be developing, it's gonna get messed up because, say for instance, when we are sending a message from server A to server B, we can send it in numerous ways. Okay, we can send the payload in encryption, we can send the payload in JSON or some other mechanisms, or other data payload types, which represent a different type of data. And there can be protocols that can be used to send. So we can use either HTTP, we can use TCP, or something like some other protocols that is available. So the standardization for message passing, so sending one message to another, should be in a way, so everyone in this industry or whoever building a parallel algorithm should get out of, okay, this in here we are working with a parallel algorithm, and when we want to share information, what we need to do is we need to share the information using a well-known protocol or well-known interface. So in order to overcome that challenge, to make it standardized, in 1992, we come with the message passing interface, or MPI, to standard this message passing implementation. Okay, so based on this standard, what we will do is, whenever we want to send a message, okay, it won't be something random. We won't be using different type of protocols. We will use this standard protocol. We will send message using this payload type. So we have the standard. Now each and everyone within the industry, or whoever want to do parallel computing, they have a mutual agreement with each other. So we'll be using MPI, message passing interface, so we can communicate with each other. So MPI is the de facto industry standard for message passing, replacing virtual all other messaging and parsing implementation. MPI work exists for virtually popular parallel platforms. So most of the parallel building platforms still we use MPI. So we have several versions of it, MPI 1, 2, 3. So we can use either, better to go with the MPI latest version if you are trying to come up with the message passing interface. But remember, this is one standard standard that is used between industry. So if you have two different industrial giants where they want to share information, okay, we are doing data exchange. So in order to make that happen, let's use MPI, then they can agree upon and work on it. But remember, this is compared to this is relatively very old technology. There are new message passing interfaces or MPIs available, not the one that we are talking in here, but there are different applications, different mechanisms where we can send information from one computer to another. So if you guys know the rise of streaming, when we work with data, now the data is not like one directional, or it is not one time thing. So when we are working with real-time applications where thousands of applications are coming in, a lot of things are happening within the applications. Now what we need to do is we need to handle the applications in not one single time, but it should be handled as a stream. So data is coming continuously. So data is not like one-time thing. We send a message and the receiving party will act upon it and we will close the connection. It's not going to be simple in modern world. In modern world, what we have is a lot of the time is stream of data. So the MPI is not that much helpful or not that much let's say up-to-date technology in terms of nowadays, but we need to know what's there in the root and how we overcome the challenges in the past. So right now we have more elegant way or more easier ways to communicate with each other. So we have RPC calls, we have what do we call message queues, message brokers, a lot of things, a lot of new technologies where we can handle massive amount of data. So we do not have to worry about data loss, or we do not need to think about working with the data exchanges. So most popular ones that we see in the real world are the example of queues. Okay, so in order to work with queues, we have protocols like AMPQ, and we have protocols like GRCP. There are a lot of things that goes around the world. So we will look in one or two, at least one of the implementations. So we will see, okay, we can send message from one end to another using, let's say, a Kafka stream, or we can send a message using a RabbitMQ queue. Or maybe we can use GRCP to send one protobuf to another. So most of these algorithms are optimized for modern day world. The payload is less, as you guys can see. The data that we are sending from machine A to machine B, if it is one single kilobyte, okay, we do not have to think about the network and the payload itself. It's very simple payload. But think we are sending 1 GB of data. Okay, 1 GB of data. So when we are sending 1 GB of data, the transfer rate matters. So when, say for example, we need to make sure the applications that we are running, the application, the data that we are sending is highly optimized, and they are not sending junk data. Think think the example of 1 GB. So if we can compress that, or if we have a better way of communicating this data from one machine A to machine B, let's say, for example, if we the 1 GB worth of data, if we can make it compressed and we can make it more efficient, and if we can send it from machine A to machine B, let's say with the correct data compression, we were able to make it 50% smaller. So the 1 GB file is now 500 megabytes because we use the right data, and we use then we use the proper networking and everything. Now the data is getting sent in effective manner. So we can save the data, we can save the cost of sending data from machine A to machine B, and we are gaining some band power because of we are sending highly compressed data. So think in a sense where we have a data center. Okay, when we are working with a data center, or we are working with a real parallel computer, which we are not talking even in gigabytes, we are talking in terabytes or petabytes of data. Sending that amount of data in a wrong format will take months. But if we can optimize those things, if we can make the application work without an issue, or without having a lot of overheads, without going into huge payloads, we can save a ton of data. So in order to make sure that we are working with data that is highly optimized, then we gain a lot of traction. So we will talk in details how we can do such communication from machine to machine communication. Probably not using MPI. We will be using something modern like gRCP or Kafka. So we will see how we can send data and receive data from one machine to another. We'll just go through the theory, and we will come to practical in later on how we will do that. Okay. So next thing that we will discuss is data parallel models. Okay, we'll look into this section once we get it. So we have this data parallel model. So we have an array of data. Okay, so in an array of data, what we are doing is, it's pretty much simple. It is like the simplest form that you can find. The application, the data itself, they are chunked down into different tasks. So if you guys can see a data containing array of A, we have a task which take data from 1 to 25, and we have a task 2 which has the data points from 26 to 50, and we have the same thing with a n number of data. So what we'll do is we will chunk down our application. We will use this application pattern in order to update the data. We get the data from a single point, and we chunk it down and work with it. So what is the downfall, or why this application is not used everywhere? The main reason is that the main reason that we are not working with this kind of application is that the data that we are talking in here from these chunks, the data should be able to process individually. The data is not having connection with each other, so no dependencies are there from point A or the task A to task B. So the data that we are talking in here should be able to work in a way that they are working independently in terms of how many data is there. It doesn't matter, as long as they are independent from each other, we can work with that. So this model we will look into like this. Okay. So may also referred as a participant global address space, PGAS model. So you guys can see that the reason behind that is we are having the data in one single global space, like what you can see in here, and when we are using that, when we are working with the global application, global data array, we will be using all the data within this global address space. So what we will do in here is that the parallel model demonstration following characteristic: address space is treated globally. Okay. The address space is treated globally. That means everyone in the task, so task A, task B, task C, every task has the access to the array, but not all the items in here. So specific task will have an access to one single portion. Otherwise, as you guys might guess, the data will get stuck, or data will get polluted if you are trying to access something out of the two different segments. So we need to make sure we are accessing only a portion in the global space. Otherwise, this will fail sometimes. Okay. The next thing that we need to do is next thing that we can see in this here is that most of the parallel work focus on performing operations on data set. The data set is typically organized into common structure such as array or cube. Okay, so we normally work with applications, or we see the data that we are normally using in typically in arrays. Okay, cubes or higher order ones are not like in day-to-day activities, but for parallel computing, that is something like we can see normally. But for simplicity, we will just have the array as we all know it. So the data set is commonly into a common structure. So the data that we are seeing in this array is going to be structured in a way. So every data within the application or within the global address space or in the array is in a single format or a particular format that every algorithm in here is accessing in the same way. So the data that we see here is in a common format. That's the bottom line. A set of tasks working collaboratively on the same data structure. However, each task work on different portion of the same data structure. So even though we have the same data structure, highlight on the data structure. Okay, so the data that we are working is in the same structure, but the data that we are accessing is portioned into different section. So single task will have a small portion of this application. Okay, task performed in same operation. Task performing in the same operation is sorry, task performing the same operation on the portion of work. For example, add 4 to every element in array. So the task that we are doing is also not going to be doing different things. So each and every task that we are doing in here is going to be one single task. So you can see the task that we are doing in the task 1, 2, and 3 is going to be the same thing. So we take the we do the operation B on data point I and multiply it by a single given data. Okay, so everyone in here is same. Only thing that we will see changing within the application is the I, that means the input for this algorithm. So in a way, we are doing the same operation. We are doing the same operation, and we are working with this application. We are working with this application, and we are performing the same task over and over. So you will see when we are going to GPU programming, what do we mean by that, and it's like the basic concepts in here. So you will see this in action. Okay, right. So on shared memory architecture, all tasks may have access to the data structure though through a global memory. Okay, so this is like fundamentally we are talking about GPU programming. So we will see the global space in action. So on shared memory architecture, all these tasks actually access the same data in this global space. Okay. All right. On distributed memory architecture, the global data structure can be split into logically and physically across tasks. So in this, we have this global data structure, but there can be distributed memory architecture. A global data structure can split the global access, but there is something that rarely happens. So we do not want to worry about that much on that scenario. Okay, the next thing that we will be talking, we talked about distributed memory parsing and data parallel models. The next thing that we will do is, of course, as you all might have get based on previous example, the hybrid model. So in a hybrid model, what we are doing is we are mixing one or two one or two algorithms or one or two programming models that we have talked, and build up something totally new. So in order to work with such thing, such a requirement, what we'll do is a hybrid model combine more than one of previously described programming models. That is obvious. Currently, a common example of hybrid model is combination of these two combination of message processing model, the MPI, with the thread model of OpenMP. So these are like the ones that we will be used in parallelizing application. These are like one simple example. So we have the message passing model. We can see that in the message passing model, and we have the thread model. We have the thread model. So we can combine those two and create a hybrid model. So when we are creating such a hybrid model, they oftenly use something standard, something that is available, and in this scenario, we have used these MPI and OpenMP for doing the hybrid model. Okay, so we can either use data parallel model with the message passing model. That is up to how we try to tackle the situation. But remember, sometimes these models would not work for various reasons, especially with the bandwidth limitations that we are having. Sometimes we can have limitations on the memory models. So there can be various reasons that this might not work. But in general, most of the time, the application would work as expected. Okay. So let's see. Let's see what we can do with this hybrid model in action. So the thread perform computation intensive kernel using local or on data on node data. Communication between processes on different nodes occur over network using MPI. So obviously, the thread perform the computation in intensive kernel using the local data. We have the local data, and we perform the using the thread model. We'll perform the local data, and when we want to send something over, what we'll do is we will communicate the information using the MPI API communication, or the message passing protocol, to send out the data and get it done. Okay, so it's a common practice that these two or more applications will get the collaboration in order to work with something like this. Okay, so remember, as I mentioned earlier, sometimes these mechanisms would not work as expected. That's because sometimes these are not compatible. Say, for example, there might be a situation where the data parallel model is not compatible with distributed memory processing due to the network issue, or the shared global space is violating something in a message passing model. So in order to avoid that, we need to make sure both of these are working in a way that they are communicating, but they should be also compatible with each other. Okay, let's go on the hybrid model. The hybrid model lends itself to the most popular hardware environment of clustered or multiple architectures. So the hybrid architecture that we are trying to come up or it's trying to apply is gonna work better or in a clustered or multi-core machines. So we will look into a cluster application development, and or we'll just use one existing cluster application and see how these things will work. Until now, remember, the hybrid application will work just as fine in a cluster environment, because of given the characteristic, the sharing of data, executing tasks on remote machines will be something a cluster computer do in an easy way. Okay. So another similar increasing popular example of hybrid model is MPI with is CPU GPU graphical processing unit programming. Okay, so we will use a message passing interface with CPU and GPU programming. We will see how the CPU and GPU are working together in upcoming lectures. But for now, remember the MPI, the message passing interface, will act a bridge between CPU and GPU, and how they communicate, how they work to achieve massively parallel things. So this is one of the examples of hybrid ones, because the CPU and the GPU most of the time reside on a single machine. Okay, in modern days, all of our applications, all of our machines probably will have something like a CPU or built-in GPU. So these machines work with one another, and these machines will have a communication platform built for us. So within the CPU and the GPU, there will be a communication bridge. It's probably going to be hardware built, not something that we will see in CPU in one single machine and GPU is another machine. It's not like prohibited to do that kind of things, but normally in a consumer grade application, consumer grade laptops that we see in day-to-day life, we will have the CPU and the GPU within one single board. Okay, so the latest Apple silicons, latest smartphones, they all have these capabilities built in. The CPU itself will have its own capabilities, and onboard GPU will have the capabilities to do GPU stuff. So the communication is done for us actually at the hardware level. We do not need some sort of networking mechanism, or something like what we see in the distributed message passing over a network, but a simple network like a bridge network within the hardware level that is happening. So in this scenario, what will happen is these CPU and GPU will communicate with each other using MPIs and message passing interfaces, and they will the CPU will send something, and the GPU will receive that and do some calculation on it and send it back to CPU. So this is like the basics of GPU programming. We'll look into more while we are doing GPU programming. So the MPI run tasks on CPU using local memory and communicate with each other over a network. Okay, so as I mentioned earlier, the CPU and GPU, CPU GPU is as I mentioned earlier, it is not bounded to a single network. Okay, you can have the CPU in one single machine, and you can have the GPU in another machine. But as I mentioned, in a normal use case where we generally used. We won't see that, but as I mentioned earlier, there are occasions where CPU just have the instruction and send it over a network, and the GPU will work. Most of you guys might have heard the term eGPUs, which gained popularity last few years. So eGPU is something similar in here. So it's say for instance, your local machine, your laptop or your workstation does not have a GPU built in. Okay, that can happen. It's not mandatory to have a GPU. There can be a GPU or not. But in a case where you did not get a GPU within your machine, so you need to do some computational task. So how you gonna make that happen? How you gonna make things work? So the eGPU comes in place where you can externally plug in a GPU into your machine and offload some of the data that you are doing to that eGPU. Okay, so eGPU is an external graphical processing unit, like what we have in storage. We have external hard disk where we can plug, and we can have some extra storage. So the eGPU is the same thing. So you have an external GPU where with some hardware wiring you can plug it in, and you can offload some tasks for your GPU to work with. So that's kind of things are available. Okay, so communication, as I mentioned earlier, is it can be either network, either the GPU, eGPU. In the eGPU scenario, it's going to be something like a USB cable or a special Thunderbolt or USB-C port. Based on any of the technologies where you can communicate with the GPU, but the communication channel should be it can be built in or it can be plugged in. So computational intensive kernel offload to GPU or on not. So basic idea behind GPU programming is there are some tasks where we need more repetitiveness or more computationally intensive ones. We will just send, okay, this task is repetitive, and the CPU is wasting time on doing that task. So why don't we give this task so the GPU can handle it? Okay, so it is totally doable. So we have some things like that in our application. So we will be using GPU to get some work done, and the CPU is okay. These are like repetitive stuff. GPU will handle it for now. CPU will focus on offloads, other things like a more serial applications, so sometimes even parallel things can be happen. Data exchange between non-local memory and the GPU uses CUDA or something equivalent. So we have something called CUDA. CUDA is a programming model or programming it's not a language programming model developed by NVIDIA. We will see some CUDA codes, how CUDA works, but in order to work with CUDA, there is a hardware restriction or hardware limitation per se. We need to have an NVIDIA GPU. So CUDA works on CUDA works on certain hardware like NVIDIA GPUs, and even with that GPUs, there are a lot of models available there. So, for example, we might need the latest graphic cards like RTX 4090 as of this recording to do some certain CUDA operations. So CUDA has is its levels as well. So you don't expect CUDA to run on the lowest budget GPU card that you will find. So based on the computing capabilities, we will look into that as well. Based on the computing capabilities, CUDA have different functionalities, different versions that support. So we will see CUDA in probably today. So we'll get into more details. So there are other common hybrid models. So MPI with speed threads and MPI with non-GPU accelerator. So these models, as I mentioned earlier, hybrid ones. You can have multiple ways. It's up to the application or application the developer who is doing to have these things in place. Okay. Right. So let's see more actions with GPUs and CPUs. Okay. So let's talk about something other as well. So in this scenario, we talked about SMPD and MPMD. So we'll talk in much more details with these things. So any questions up until this, guys? You have any? I think these are like probably the theory, easy ones. But in any case, you have any questions? Okay. So let's into SMP, MD, and MPMD. So so these are like the theory behind the programming models that we are talking about. So we will look into single programming and multiple data. So the term must be very very familiar. Okay. Single program, multiple data. If you guys can remember earlier on, we talked about this something similar, but remember, we are talking in different contexts. Okay, we are talking in here with the programming models, but we talk the same kind of scenario. We are talking about the we're talking in where is that? So we are talking of in here is programming models. We are talking in programming models, but the concept that we are talking in here is single program, multiple data. But if you guys can remember earlier on, we have this same thing like in hardware level. In hardware level, we talked about SISD and MP and MID. So we have single instruction and single data. The similar one is single instruction, multiple data. Okay. So in here, we are not talking about in hardware level, we are talking about in software level. So the term in here, the change that we will see is the use of instruction. We are not going to call it instruction, but in program, we are calling it program. Okay. So that's the difference that you will see in mainly. So we talked about single program, multiple data. So in here, SMPD is actually a high-level programming model that can be built upon any combination of previously mentioned parallel programming models. Okay, so this is something that programming level should handle. So it's a programming model. So it's something like the hybrid model, but the implementation wise is coming to a combination of previously mentioned programming models. A single program or all tasks execute their copy of the same program simultaneously. This program can be threads, message passing, data parallel, or hybrid. So in a single program, what we are thinking in here, a single program, all tasks execute their own copy of the same program. Okay, so the mental mind or the mental model behind the application is same like what we see in single instruction. In here, what we are talking is a single program. Okay, not something like we are using in the application. We are talking about a single program. Okay, so the single program execute the own copy of the same program. Then the term that we need to highlight in here is the same program. So as a single instruction, we have the same program run simultaneously. This program can be a thread, what we have talked in here, whether it can be a thread or a message passing or a data parallel algorithm like the global data space that we have talked, and or anything like hybrid. So, but anyhow, the instructions, the program that we are running, it's going to be the same thing. Okay, and multiple data, all tasks may use different data. So whatever the model that we are using, okay, whatever the data that we are using, whatever the model that we are using, but whatever we will be using, we'll be using multiple data or different data to process. So the program will have the single execution, but the program sorry, the program is going to be the same, but the data that we're going to be feeding to this program, each and every program will be different. Okay, SMMD, SPMD program usually have necessary logic program into them, allow different tasks to branch or conditionally execute. Only those part and program we designed to execute. That task does not necessarily have execute the entire program, perhaps only a portion of it. As it suggests, logical programming into allow different tasks to branch or conditionally execute on the part of the programming they are designed to execute. So when we are running into SMPD, the main difference that is it can execute conditionally or it can execute only a portion of the program. So it's not going to be executing the whole thing, but a portion will be executed. So this is the important point of SPMD, and usually this helps in executing the application. This helps the application execution by similar or small portions. Okay. The SMP model using message passing or hybrid programming is probably the most commonly used parallel programming model for multi-node use cluster. Okay, so using message passing or hybrid programming, and the using message passing or hybrid programming is probably most common parallel programming model in multi-node cluster. So this is like the most common structure that you will see. So it is used in most of the applications that you will use. Okay. All right. The next thing that we'll look into is the multiple programming, multiple data, MPMD. So like SMPD, MPD actually a high-level programming model that can be built upon any combination of previously mentioned parallel programming. Of course, that is obvious. So we can have multiple programming models as we like, but the change come in with the data. Okay. So multi-program tasks may execute different programs. Simultaneously, the programs can be a thread, message passing, or data parallel hybrid. So the task will be not a single one. It won't be executing one single task, one single program actually. The program will be different. It can be either one of these, or it can be all, but most of the time it's going to be a mix and match on everything. So it can be a thread model, message passing, or a data parallel, or even can be a hybrid one. So it differ from what we are using. So what we need to think in here, what we need to think in terms of these applications are that it is not bounded to like have one single type. In as we mentioned in here, it can be multiple ones. Okay. It is like optional. It is like optional that everything will be in the same type. That is coincidental. But if it is all in the same programming, it will like resemble a SPMD. But in MPMD, there is no restriction like that. It should the program can be multiple. So yeah, we talked about SMPD, and let's take this MPMD applications are not common as SMPD applications. Obviously, the main reason behind the problems that we have in the in this application is not that much practical in real life. So we are trying to resolve something in real life, but these kind of practicals like multiple data and multiple programs, it is not something that you see in day-to-day life. So in order to accomplish something like this, in order to have these kind of capabilities, these kind of applications, so we'll be not having these kind of programming models. So the usage of MPMD is very rare. Okay, it's going to be highly sophisticated ones. Even that happens, even if that kind of thing is there, it's going to be something very niche. Okay, not every day that you will see this kind of applications. So what kind of applications that you will see in this kind of situations? It's decomposition, like particularly these themselves better to function in decomposition than domain composition. So it's like not everyday use that we see, but something that most of the time we will not encounter. So we are on safe side on usage of MPMD. Okay, so it's the same thing that we will see in MIMD. Okay, mind the eye. instruction level. So it's like highly impractical to have these kind of applications. Okay. All right. We talked about the hybrid model, MPSD and MDMD models, MPMD models. We talked about distributed memory. We talked about thread models, and so all the parallel programming models we have covered so far. So what we will do is we will have the most interesting section of the this course, that is the GPU programming. Okay, so this is like where we need to talk in much more detail about the applications and what are the things that we're going to be doing within this course section. So anyone have prior experience on GPU programming? Raise your hand, please, if you have done anything related to GPU programming, at least. I have worked with GPU programming or something like that. No, so that's kind of obvious. Like the main reason behind that is unlike CPU programming, like what day-to-day programming is that we do normally. CPU programming, the programming that we normally do, we think, or what we do in a normal application is what we call the what we normally do is what we call the CPU programming. Okay, we don't add the term CPU in front, but what we normally do is the CPU programming. Okay, the CPU programming involves in different in different areas like web designing or IoT. Those kind of things are basically CPU intensive works. What we do, but when we are developing anything, we work with the CPU itself. Okay, but GPU programming is more or less is something very special, very unique in programming. The reason behind the GPU programming is the uniqueness comes with the applications that we are trying to resolve, the applications that we are trying to work with. So based on the application type, we are stuck with the applications we're going to be developing. So, for example, not every day that we get to work with a GPU. Okay, so anyone have seen a GPU? I mean, at least I know a GPU, at least a brand or something like that. Graphical processing unit. Anyone have seen it? Do I need to show it as well? Hardware, at least. Rashmika, have you seen a GPU like in physical? Okay, yeah. So it's not like magic or black voodoo magic. You will probably have seen GPU throughout your lifetime. It's the equivalent of highly processors combined into one single cooling fan. That kind of feeling the most of the time that we see. So give you an idea, the latest graphic cards that we will see, NVIDIA RTX 4090. This is like the absolute beast when it is coming to GPUs. So if you guys want to get your hands dirty and you have this amount of money, GPUs are not cheap per se. It's $160, approximately 160 US, not 100 US, D to LKR, around 5 lakhs. Okay. So if you have a good amount of money that you can spend on a single GPU, these are the ones that you are working with. So GPU initially came, as its name suggests, it's coming as a graphical processing unit. Okay, so now GPU has gone far beyond that graphical processing. The applications with GPU are now shifting towards different areas other than graphical processing. For example, in the world of AI and cryptocurrencies, GPUs are the king. So without GPUs, you can't have an AI model trained on. You can't have the massive language processes or any model that you are interested in. Those cannot be executed. So initially, what we can see, normally we use these in general market, in generally when we are using the applications, the GPUs usually comes in handy with gamings. Okay, if you want to do a game with a lot of refresh rate, a huge refresh rate, and you want to have screen recording on, you want to stream at the same time. So all those processing, it's going to eat up your memory. So to overcome these things, to overcome with the applications and complications and everything, what you will need is a GPU to offload these stuff. Okay, so there are like nice features it adds. Now, for example, this is one of the examples from NVIDIA itself. So we have these nice, we have this game, okay? We have this game, but with GPU acceleration, you can add more detail to this application. You guys can see it's more, it's look more realistic in this GPU accelerated ones. So rather than showing something the more believable, will make the gaming experience much more better. So we have FPS, frame per seconds. So with the latest frames, you have more frames. That means the number of frames that you will see within the monitor is gonna high, and that's gonna improve the looks of it. When you are looking at the application, it's gonna be like crystal clear, and these things will have more response time. That means a player can react very very quickly. So that's kind of things will help us doing more graphics. But in other than games, other than playing your latest game within your machine, there are other applications, as I mentioned earlier. We have the full capabilities of our GPU for other non-gaming experiences, for AI, Bitcoin mining, or cryptocurrency, that kind of things. We are also using GPUs. So why GPU is so important in modern day programs or modern day things, and why why a GPU is like something that we need it in our machine. So anyone have an idea apart from gaming? Okay, apart from gaming, why do we need a GPU? What's the reason behind having a GPU in our application within our computational task? So we have a CPU, very powerful CPU that we can work on. Then we have also a GPU. Most of the time we have it for gaming, but other than gaming, right now, most of uh, machines that we are coming with, they are coming with GPU. So what kind of purpose a GPU serve? What kind of things a CPU is good at? What kind of things is a GPU is good at? Anyone have any insight on why do we need a GPU? I think we did a assignment on it. Anyone can refresh their memory? Yeah, the data mining is one of the applications. Yes, that is true. But I'm asking why data mining can't be done in the CPU? Why can't we do it in the CPU? And why do we need a GPU in the first place? Why can't we do everything in CPU? Why do we need a GPU? GPU and CPU both are doing computational tasks. They are doing the same thing, doing the computational task. So why do we need a CPU and a GPU? Any guesses? Okay. Let me take one single example from real world. And remember, this example is not to be offending anyone or like to harm anyone perspective of their jobs. I'm just simply stating out the um, things in a way that you guys can understand. Don't get offended or don't think less of me by giving these examples. Okay. So the let's talk about the CPU. The CPU is is capable of doing many things. It can do serial execution. It can do parallel executions. So anything that comes to CPU, CPU is more than capable of handling uh, different task, different instruction. They have the ultimate execution strategy. So we can give multiple instructions. Those multiple instructions get executed in parallel or serial way based on the algorithm that we are playing. But the CPU can switch context very easily. That means while we are executing one single program, it can hold that and execute another one in the same time. Okay, so the instruction may change. Okay, because of the context change. The first instruction was addition, the second one was subtraction, the third one will be another addition, the third one will be another operation. The operation that we are doing is gonna change. Operation that we're gonna be performing, it's gonna vary on each instruction on a CPU. Okay, so the CPU is capable of handling many things in this context. Okay, so let's take a real world example. You guys know when we are doing programmings. Okay, I'm talking about general programs. So here, okay, when we are doing programming, there are certain people who are extremely good at it. Okay, we call them as general programmers. Like, for example, we will find someone who is who is um, capable of doing the backend development only. So if you need something to get done, the backend developer, something related to backend, the backend developer is the ideal person. But is he good at developing front-end applications? No, that is something that we can't expect from a front-end developer. The front-end developer might be the backend developer might be lacking behind, or he might struggle with doing certain tasks. The backend developer is good at doing a certain task at a certain speed. Okay, if we give some backend task, he will definitely do each and every one. That is a repetitive task. They can do that. But there are another set of programmers which we call full stack developers. So in full stack development, what they can do is they can develop backend, they can develop front end, they can do CI/CD pipelines, whatever you name it, anything related to programming, they might be able to do that, and they can easily context switch. Okay, so they have the context switching capability where okay, I am doing a backend program, now I want to do something in the front end. They can context switch very easily. Okay, so in a scenario of the full stack developer, they can do multiple things. They can do application switching. They can do database migration. Anything that you throw at them, they will be doing that. Even the context switching. Okay, while I want to change the front end, they can easily change that one as well. So what's the difference between those two programmers type? The full stack developer is good to do context switch based application where they need some context switching to happen from front to back end and those kind of things. And the backend developer is good at what he's doing the best. It means developing backend only. So in a real world situation, the in real world we can't, like, the people's capabilities change on one another. Okay, one single person might be a full stack developer and a better backend developer. That is true. And a backend developer might be good, but sometimes they might lag behind a full stack developer. That's like in personal, like it's the human nature of it. But in terms of programs, in terms of hardware, CPU related stuff, that is not the case. So they have the CPU and GPU. They have completely two different jobs. The processing powers, the things that they do, is differ to one another. So they have the computing capabilities at the best. Okay, CPU is at best context switching, changing everything and doing each and every task. But in GPU is sophisticated. GPU built on doing one single task. Okay, at a given time. Okay, at a given time, not all the time the same instruction is going to be executed. No, at a given time, the GPU is only performing one single task. Okay, so as I mentioned earlier, in the human example, the backend developer might develop the application very fast because all he only need to think about is doing backend development only. Okay, he do not need to think about front-end applications, database, or anything like that. Database optimization or something like that. Only the backend development. So the set of instructions, what the developer should do is gonna be the same thing, or the same thing for all the instructions. It's gonna be the same thing. Okay, for the backend developer, They are more focused. They are only working on one single thing. The context switching happens, a full stack developer, they might put something in hold and they need to reload it again. They need to offload certain things. They need to load it again. In human nature, you might get more interference, but in a CPU, in hardware level, they do not like get tired or something like that. But in nature, the context switching will give us a little bit of overhead, loading, offloading, that kind of thing. And since it can perform so many things, it might not be good in executing every time the single application or single instruction. So CPU shines where the complexity of the application is very high. In GPU, it is not the same. The GPU will be performing the same application, same instruction set, but the data is different. So I'm not sure how many guys have seen NVIDIA demo on this. I don't think I have that. Okay. I'm not sure whether you guys have seen the CPU and GPU, and let's see what is the difference in real life. What do you understand by what is the difference between a CPU and a GPU in doing the same task? Okay, so this is one of the videos, CPU versus GPU. Okay, so let me change the settings so you guys have. Okay, it's not sure the quality of the video is that much, but you'll get the idea. So we have the robot, okay, one single robot. One's represent a CPU and the other one represent a GPU, okay. So this both of them are going to be doing the same thing, that is drawing a picture, okay, drawing a picture, drawing a circle. So in a CPU, what we get different instruction, because CPU is going to be the CPU's handling way of handling is like, okay, I get an instruction, I execute it. I get another instruction, I got to execute it. Yeah, and the CPU moves on in a way at a given single time. Okay, I'm talking about in here at a given single instance. It takes one instruction and execute it. Okay, so you might say, okay, if one single CPU having one single thread or one single core, that is true. Okay, so at a given time, if we have one single core, one single thread that can handle execution, this will be the output. Okay, we get a one single instruction, we get one single data, and we process it. If we say, for instance, we have four, that means we have four of these. What will happen? Four of these. Okay, four of these, what will happen is there will be four, and four of these will send that kind of information, or the projection that we are doing, processing on one single processing, is up to 4 times. So if you have four, the dots will not only one dot will happen, but four of these dots will happen, but we need to make sure the data don't collide in each other. So this is how a CPU would draw something if it is a one single core and one single application. Yeah. Okay, so one single instruction. So you guys can see there is only one core or one CPU, one processing unit. So it is the expected behavior. But for other cores, as I mentioned earlier, if we had four, the drawing can be 4 times faster, because we have 4 cores that is doing the different job. But at a given time, this is the expected behavior. And for a CPU, it is the same thing. Okay, at a given moment, okay, at a given moment, what we're gonna do is we will have we will have processing units. We have the same instruction, that is the paint instruction in this scenario, in this hypothetical scenario. The instruction is paint, okay? But in the CPU, we had only one capability, one processing unit. But in a GPU, what we have is same instruction, but we are executing that instruction not by one single core or one single instruction set, but we are executing the same instruction in so much more cores. Okay, we are not executing one single instruction. We are executing one single instruction, not only one core, but in thousands. Okay, so you guys can see ultimately the CPU had only one instruction executor. In here, one single dot pusher that you can see it in here. In the GPU instance, we have thousands. If we have 1,000 guns, we have 1,000 cores that we can spare out. Okay, so in a scenario where GPU shines, when the GPU works, so we have a lot of execution programming units, lot of execution units will be executing the same instruction. The instruction is going to be same, the data might be different. So if you take the example of this, okay, let's take the CPU one. So the CPU instruction in here, the CPU instruction is paint. Okay, the CPU instruction is paint. So that's what it is doing right now. And the data it receives, the data that we are getting in here is color blue. Color blue is the input. Okay, we say print color blue 1, color blue 2, color blue 3, and this kind of things. Okay, so we are giving the instruction paint to this CPU, and it is doing one by one. And in terms of this GPU, or in GPU world, what we are having in here is the same instruction. Each and every single instruction executor in here has the instruction of paint. So there are like huge tubes here. You guys can see all these single instruction execution will have the same thing. It's called paint. And the data that we are getting in here, the data that we are feeding in here is going to be different colors. It can be RGB. Either one of these colors will be the data input. So all the instruction that we are executing, in here is going to get executed at one single time. The data will be different. Okay, so the main advantage of a GPU is it's execute a lot of instruction, a single same instruction at a given time, but with different data. So these are ideal. These kind of processing power is ideal for graphics. Okay, how? You guys can see that in the same example that we saw last time with the gun. So our screen, our computer screen, what we see in here is a collection of pixels. Okay, we need to render each and every pixel that we see in here. Okay, so in order to process these pixels, let's say in my machine, in my monitor, I have only 3 by 3 pixels. So my pixel ratio is very bad. Let's assume that I only have 3 by 3 pixels. That means only 9 pixels are available for me for a given modern day computer that is like very small. Modern day computers will have approximately approximately more than thousands wide and like 700 big. That's kind of resolution is going to be there. So many pixels going to be there. So based on your resolution, you can find how many pixels are there. But for now, we will assume we have only 9 pixels within our machine. So in a CPU rendering, to render out those 9 pixels. Let's say we have 3 cores that we can work with. So with 3 cores and with a given single instruction, let's say we are all using these 3 cores to render out our 9 pixels. So what we'll do is within we'll assume 1 second will take to render out 1 pixel. Okay, so we have 3 cores and we have 3 by 3 space to fill, and we have 3 cores, and as you can assume, all the cores are working for rendering out this content. So what will happen is the three cores will take 3 seconds to fill out the 3 by 3 or 9 pixels. That's because each and every core is working, taking 3 seconds to draw 3 pixels. So the first second will draw 3 pixels. The second and the third one will also draw 3 by 3 and 3. So altogether, to draw the 9 pixels, what will happen is it will take 3 seconds. But if we have 9 cores, what will happen? The execution time is going to be 1 second because of the 9. There are 9 cores, and we can give all the 9 instruction for the 9 cores, and they will process it. And within 1 single second, we can get the process output as we expected. Okay. So if we have 9, then we have 1 second. If we have 3, we have 3 seconds. So the more cores that you have, you can get the information done. But say, for example, we have 12 cores. Okay, now we have 12 cores that we can execute. Is it going to improve that much? Okay, that's not going to be a case because we have 9 pixels to draw, and 1 pixel can be drawn by 1 core. So we have 12 cores, but the problem is we only have 9 to fill. Okay, so rather than that, we do not need to fill other pixels because they are not existing. And since they are not existing, we do not want to render those things out. Okay. So more GPU does not mean more work to be done. Okay. Even though we need 9 pixels to be rendered, 9 cores will do. Okay. Having 12 cores will not have an effect because more cores, there will be free cores that will not execute anything. So the bottom line is let's say for drawing this resolution, my resolution is around I think 2500 by 1000 or something like that. So that is the resolution that I need to work with. So if I use a CPU and a 12 core, let's say I have 12 cores within my CPUs, and the amount of pixel that need to be processed is coming to that 12 cores. But if I had a GPU as the same size as my display resolution, what would happen? With one single instruction execution, the GPU can handle it by 1 second. Okay, so if I have a GPU that need to be accelerating my videos, what I can do is, okay, rather than giving 12 core CPUs to do the job, I can give a 1000 core GPU to get it done instantly. Okay, so then what will happen is it will work, it will execute that and give me the result way more faster than a normal 12 core CPU would do. Okay, so then you might think, okay, if everything can be joined, everything can be accelerated within GPU, why don't we put everything in GPU? So normally we do not need a CPU. So everything that we need to do, let's put it in GPU and get it done. Well, the other trade-off come in this scenario, that is executing the same instruction. So GPU is good at executing the same instruction, yes. But if we have multiple instruction where we need to switch the context more oftenly, the GPU will fail. The GPU is not designed for context switching that much rapidly. So we have the GPU rendering out, or in this scenario in in this scenario outputting a video, the GPU is only performing one single instruction, paint. Okay, I'm not literally saying that GPU is doing execution method called paint, but in reality, let's have abstraction. The only instruction that GPU is running on right now is paint. Okay, so whatever the data they receive, they only do paint. Okay, I will paint this amount of this based on the color, based on the map, or based on the input that I get. So we can have multiple data, but the only thing the CPU is doing is paint at a given time. Okay, all the CPUs are doing all the CPUs. I'm talking about all the ones that within the GPU is going to be. It's not going to be the cores or something like that. We will have more detailed discussion. What do you and what are the execution units in GPUs? But for now, let's assume that is similar to the CPU cores that we are having. So whatever the instruction that we need to run, the application will be only executing one single command. So that is a disadvantage in terms of CPU. The CPU has the way of context switching very oftenly, that they can handle multiple tasks. So for example, while the GPU is only doing paint, the CPU can have multiple context switches, paint, play sound, connect to internet, that kind of multiple instructions are better with CPU. Okay, so the mental model behind the CPU and GPU is that CPU is good for context switching, and the CPU can take simultaneous jobs, and CPU works as its intended. On the other hand, the GPU has some different mechanism. The GPU is good, but to execute one single type of type of thing. So in a computer, so we need to balance these things out. Okay, so what we do is, in let's say normal consumer grade machine, the CPU will take care of doing the context switching, all this stuff, while the GPU will handle rendering images and all this. if the GPU, if the CPU also can do the the UI rendering stuff, the problem is that it is not going to be good as a GPU does. So in order to avoid, in order to offload some of the tasks that CPU has to do, okay, the CPU might need to now do GPU, the screen rendering, context switching, and all those things. But what if we can offload some of that task? The CPU is not do not need to worry about the rendering screen stuff. That thing will be handled by the GPU, and the GPU is doing a better job at it. At it is because the given instruction is the given instruction at the moment is executed by the CPU. So the CPU is doing context switching while GPU is doing the rendering stuff. So that is the mental mind behind CPU and GPU. And why can't we put all the things in GPU? Why can't we put all the things in CPU as well? So CPU is capable of handling these things. Yes, CPU is not incapable of doing instruction execution. It is, but the problem is the slowness, the context switching, the effectiveness of it. GPU is also capable of context switching, but again the problems comes the instruction loading and instruction offloading. So to sit in the middle, what we can do is we use CPU for certain stuff in a normal machine like what we are using today. The CPU will be taking care of the kernel, the CPU will be taking care of the context switching, playing sounds, and everything else in between. While the GPU, on the other hand, will take care of things like screen rendering and anything that has single instruction but multiple data. Okay, so offloading is the balance in that we are finding in here. So GPU will do most of the repetitive task in its core, while CPU will do context switching tasks in its context. Okay, so GPU is designed for that purpose, at least at the beginning. Now, in terms of cryptocurrency and all this stuff, the GPU comes back. The GPU comes back because in cryptocurrencies, what the process called mining is going to be the same instruction. It's going to be the same instruction all over and over again, but the data are going to be different. Okay, so that's why in order to mine or in order to process things in Bitcoin or cryptocurrencies, we use GPUs. Okay, the GPU can do the execution, the same type of application execution very good. So that's why cryptocurrencies or Bitcoin miners use GPUs to get the computational work done. And other things like where GPU shine these days is the world of AI. Okay, so AI, artificial intelligence, is also doing the same instruction set in a nutshell. Okay, I'm not telling you AI is like doing GPU programming. No, in a nutshell, in AI programming, what will happen is we'll be executing the same thing, same application, same instruction set on different data. Okay, the underlying the task behind AI is going to be, okay, I'll be executing the same instruction, but it's going to be so many different data. Okay, so that is the mental mind behind using these applications using these things in our machines. Okay, so make sure that we have these applications, we have these use cases in the real world. Okay, so the GPU is doing the same application with different data. The CPU is doing different application at the same time. So the GPUs were historically used for enhancing game graphics. Obviously, you guys can see that the screen is painting whatever we are painting in here. That is the only thing that screen is used at. And the GPU can help with that, because paint method, we have to only use the paint method. We just need to have different data. Gaming, this 3D displays and designing software. GPU accelerated computing refers to parallelism and enhancement of using GPU and CPU processing power together to computationally expensive mathematical operation like matrix operation, ray tracing, and 3D rendering. So one of your what do you call the assignments would be thinking about or get a report about these mathematical operations like matrix operations, ray tracing, and 3D rendering. So get me a small description on these three languages, also these three mathematical operations. See the operation itself and see whether the same operation is going to be applied in matrix operations like matrix multiplication and matrix addition. Are we doing the same instruction set for a matrix operation? Okay, let's have a look at it. What do you understand by ray casting? And when you're doing ray casting, what sort of mathematical things happen? What sort of things it should happen? Same goes to 3D rendering. When we are 3D rendering, okay, we are creating something, and what sort of thing happens to make it GPU accelerated? What sort of things that it makes? Okay, 3D rendering is a mathematical operation. Okay, have a look around those three, and we'll get into those mathematical stuff. The next thing is compute unified device architecture. Compute unified device architecture, or we call it for short CUDA. Is an NVIDIA developed platform for parallel computing and parallel computing on CUDA enabled GPUs. Okay, so NVIDIA initially go ahead with designing graphic cards. NVIDIA go ahead with developing graphic cards. So these graphic cards are like earlier days, it was like GPUs are meant for accelerating games and everything, but then they have seen a potential market like the CPU market. We have the GPU, not we can use this not for only gaming but for other applications. Okay, like especially with the parallel computing. Okay, so then NVIDIA thought, hey, why don't we just we use these nicely perfectly working GPUs in other applications. Okay, so we have the parallel computing, AI, and all those things. But the problem arises when we are developing these kind of applications. It's not going to be easy. Okay, we are going to be handling not only graphical processing but other processing as well. So in order to cater that, in order to make sure that, okay, we can do more than graphic processing. We check out this programming language, which you programming architecture, which you can use, which we can use to develop parallel algorithms. Okay, so the idea with CUDA came along. So if you want to develop a parallel algorithm, and that parallel algorithm has an NVIDIA GPU on it, once you enable the GPU and your hardware component, what will happen is you are able to develop parallel algorithms using this CUDA architecture. So you have the supporting methods. You don't need to reinvent the wheel. The CUDA will have certain functions, certain things that is controlling the device itself. The control to its hardware features will be given by this Compute Unified Device Architecture, or CUDA, a piece of software. And as I mentioned earlier, there are different CUDA versions. Let me check. CUDA versions. Okay. CUDA version. Okay. So we have something called CUDA Dev Kit. Okay, this is where like you get the latest CUDA things. So if I go, I will be Linux architecture. I will use architecture. Let's say ARM-based one, and compilation, distribution. These are like related to what we are going to be installing, and it's not having the version. Here, let me check. I need to find the computing. So you guys can see different CUDA versions. Okay, so in different CUDA versions, they are starting from 12, at least that is like the latest, and we have up to CUDA 11 support. So each and every these CUDA versions have different computational computational level. That means not all the features are going to be within your local GPU. You need to have a certain GPUs and certain number of GPUs you can handle with the CUDA. So not every CUDA version is capable of running on each and every hardware you will find. The hardware that you buy has limitations. Okay, not gonna be like how many VRAMs are there, how many cores are there, how many things that you can do. Based on that, the capabilities of the card change. Okay, so there are some cards which have low things, that low level of cores are there, which is like the budget versions of NVIDIA cards, and there are more high-end ones where it has more cores, more computational things can be done. So in a place like that, the CUDA has different versions, CUDA versions, and different CUDA version can be installed in different hardware. Okay, most of the time those are common. For the latest and best ones, you will have the latest CUDA version, but you have an older version like I have with my other laptop. I think I am stuck at CUDA version 7 or something, because it's very old laptop and the CUDA version, it's supposed is really old. Okay, so we cannot get the computation capabilities going forward unless we have the latest one, because latest one have latest improvements that they have done, more and more cores, and you can get it done pretty much easily with the latest versions. Okay, but the cost you have to bear in mind as well. So to make parallel computing easy, they have introduced CUDA. So the CUDA is it's not like a thing that you can install without a GPU. Of course, you need a GPU, and the version, as I mentioned earlier, not all the CUDA versions are supported in all the cards. You need to have a supporting card and a supporting version, and it is the CUDA program itself. It is closed source, so we do not know what sort of things happening in the CUDA itself, CUDA architecture. We can just use it from our end. Okay, and the CUDA, the things that we write in CUDA is using low-level languages like C or Python. Okay, so if you want to write some parallel algorithms, and those parallel algorithms need to write some program. Okay, I need to write a program for my parallel algorithm. Even if I am using CUDA, I am stuck with C, C++, or Python in this scenario. There are other language supporters for Fortran and all, not that much popular these days. C, Python, those are the two main languages that has the support for CUDA language, CUDA architecture. If you want to write something for CUDA, to parallelize everything, you have to use C, C++ with the CUDA. Okay, so we will use the CUDA programming architecture. Okay, do not get confused this with the hardware architecture. Okay, remember the name. Pay close attention to the name itself. So when I'm asking about, okay, I need to know the CUDA hardware architecture, and you have a different view. If you want to give the CUDA programming architecture, that is this view. Okay, do not get confused those two. Most of the time what I've seen is when I ask to write something like that, students keep having things, what do you call, having these things mixed, or they get confused between these things. So make sure the CUDA programming architecture and the CUDA hardware architecture are two different things, but they have more than similar things in mind. Okay, so it's going to be a little bit challenging for you guys to remember the hardware and the programming architecture. So CPU architecture is meant for sequential execution of complex controls, equations of data or management. That is true. That's what we have learned. GPU architecture is meant for parallel execution of simple logics. Okay, so these two lines represent what CPU and GPU stand for. So CPU is complex execution handling. GPU is simple execution handling. GPUs are not standalone systems, and CPU, a host, together with a GPU, a device, forms a heterogeneous computational platform. Okay, so Say for instance, I need to run a GPU, but remember, I can't run only the GPU. Okay, the GPU only process is not possible. So if you want to execute something in GPU, you need a CPU to host it. Okay, so from now on, if I'm talking about the host, that means I am talking about the CPU machine, where the CPU machine is. If I am talking about the device, that is the GPU that I am talking, and we'll keep those two acronyms or those two references in mind. Okay, so GPU cannot run standalone. It needs a CPU to operate. Okay, so GPU is, as we mentioned, simple, but so many tasks are executing, and the host, the CPU, is in connection with GPU to get works done. Let's see how it is done. How CPU and GPU, or the host and the device, is doing its job. Okay, so let's assume that by using a normal hardware or a motherboard, you were able to plug it in the GPU, and the CPU is correctly mounted to your machine as well. So we have the CPU and GPU. Now what we need to do is we need to check how these things are communicating with each other. Okay, so CUDA compliant code has two components. So any CUDA code that we are running has mainly two components that we can see. If you are writing something to get GPU accelerated, there are certain two different code sections, or two code sections that you can clearly see. Computationally light CPU host code and computationally expensive GPU device code. So we have two codes, the CPU codes or the host code, and the device code, which is computationally expensive ones. Okay, so CPU do not get that much of work to be done, but in a GPU you have much more things, more complex tasks to be executed. Okay, a CUDA program has separately defined CPU and GPU code. So in the program that we are going to be writing in CUDA, we have two different sections that clearly can see the CPU code and the GPU code. Okay, the GPU code consists only of the functions that are going to be parallelly executed on it. Okay, so when we are going to GPU code itself, the GPU will have only codes that is executable there. Okay, and that performs a CUDA program CPU functions that are going to be there. OpenCL is the open source version of CUDA and runs on CPUs and GPU almost vendors. So one other thing that we should notice is that we have alternatives to NVIDIA's CUDA. We have OpenCL. Okay, so OpenCL is one of the GPU vendor unlocked programming architectures. Okay, as I mentioned earlier, CUDA is vendor locked to NVIDIA, but OpenCL is not. OpenCL can be run on NVIDIA or any other GPUs, while CUDA only runs on NVIDIA GPUs. Okay, so one thing that we need to make sure that OpenCL is good, of course, if you are into other if you're into other programming models. Okay, so other hardwares actually. So OpenCL can run on other hardwares, like not only NVIDIA, there are several other GPU manufacturers like AMD Radeon is one of the GPU processing or the GPU devices that you can find, AMD Radeon series. Okay, and there is a new Intel Arc, if I can remember, Intel Arc GPUs are there. So there are like different things, different hardware is available to use as well. But NVIDIA is vendor lock with CUDA, but OpenCL is not. Okay, it's an alternative to CUDA, but we will not be covering OpenCL code in this section. We'll be primarily focusing on CUDA and NVIDIA codes. Okay, and let's see how GPU and CPU is architecture out in programming level. Okay, this is, remember, as I mentioned earlier, this is the programming architecture. Okay, not the hardware architecture. Okay, so we have this code execution section. So we have the CPU have DRAM, and we can have cache, like what we have seen. And we have the host CPU, that is CPU core 1, core 2, and so many cores are there. So there is the PCI bus express, okay, PCI bus express, which we use to communicate with these two hardware. So in a typical GPU, you will find a device memory and devices, okay, because these devices, and those devices are consisting of things called threads. Okay, so we have CPUs and cores. In GPU, we have threads. Okay, so we do not see any cache or DRAMs available, only the DRAM, that is device memory, for the GPU. So when we are talking about the capacity of the GPU, we are talking about the GPU DRAM memory. Okay, let's say let's take NVIDIA RTX 4090 memory. Okay, so it has a DRAM of 24 GB. Okay, so in this scenario, the GPU is having 24 GB of DRAMs. Okay, that is compared to most of the graphic cards, it's way huge. Okay, all right. So what we have in here is the memory model, or what we can take around in this application is this simple architecture. Okay, so the communications happens using PCI bus. Okay, let's see. During the execution of CUDA code, memory exchange happened between the host and the device. The device execute the code, then return into the result to the host. While the normal C+ code has C prefix, CUDA has execution of CU and USO in VCC compiler. So in here, remember, when we are talking in here with the application, the CPU first initiate the work. The CPU is starting the execution and everything, and the CPU is having the execution started, and what will happen in here? What will happen in here? The CPU is starting the execution process, okay? And once the data is ready, we copy that data into the GPU, okay? We need some data to be executed. The instructions, the data that we need to run on GPU, first we prepare it, and from the CPU, we copy that into GPU. So once the GPU is capable once the CPU is copying this code to GPU, and the GPU has the execution done. Once the execution, everything is done, the GPU then again back copy. Okay, I have completed your task, and here's the result. The CPU is getting back the result. So that is how a normal or a typical application works. Typical application works like that. It's the simplest form, and the only thing that you guys need to remember, first, the CPU is starting the execution, okay? And once the CPU execution has done, CPU execution is done, like preparing the data, copy everything to GPU execute it, and once the GPU execution is done, it returns to the CPU, okay? So we will look into this application, how in terms of C, how we can look into these things in real world. Right now, we will have more and more look into the application. Okay, first thing that we need to do is that we need to look into the things that we are working with, at least with what do you call it, with the applications. So we need to learn few of the terms or few of the things that makes up the application, or makes up the terms in CUDA programming. Okay, so we will come across these terminologies. Okay, a grid, a thread, and a warp, those kind of things. So we need to know, okay, what each of these things means and what sort of things it is resolving. Okay, let's see these terminologies, and we will look into the CUDA stuff. A grid is a collection of threads of parallel cores running in the MOS at the moment spawned by a single compute kernel. Okay, so we will have the highlighted things here. We need to know a grid is a collection of all parallel cores running in the spawn single compute kernel. Okay, so we have these things called kernel, we have things called grid, we have things called threads. So right now it won't make any sense at this point, so we'll skip around these things, and we will get back to these things once we talked more and more. Okay, so for now we have these things called a block. Okay, block is containing few things, a threads, a few section of thread, and we have 1D and 2D blocks. We will look into those things as well. So we normally work with 1D and 2D blocks in normal application, but for AI application, we will definitely go with 3D blocks as well, because a lot of the data that we are representing in AI is going to be 3D, or what we call those things as a tensor. So we will look into these the words in a different in upcoming lectures. But for now, things, the most important things like threads, blocks, just have it in mind, the kernel and everything. Okay, the next thing that we need to do is that we are working with CUDA. We need to know the CUDA terminologies. Okay, these are like the fancy words that you will find in CUDA. So make sure you know these things at the best. So so first thing that we need to do is the term host. Okay, the host is the CPU and its memory. So when we are talking about host, we are talking in here. We are talking in here we are talking in here the machine which the application is running. Okay, so first thing that we need to do, first thing that we need to make sure the host is the machine that we are running. As I mentioned earlier, GPU cannot run individually. GPU needs a CPU to host it. So the machine which the applications run in, the application that we will be executing, is called the one with the host. Okay, and the next one is the device. Okay, in simple term, the GPU, what we are referring in here, is called what we call the device. Okay, so whenever we are saying the word device, we are referring to the GPU itself. Okay, and the next thing that we need to do, is that know the term streaming multiprocessors, or SMs. Okay, independent processing unit. Each device contains several NPs. Okay, so stream multiprocessors we will look in more details, but for now, remember individual processing units. It's like this, not the smallest one, but a set of a level of computational units that we can think of. Okay, so in this scenario, we have some other things like compute capability, or CC. This is the one that I am talking you guys over and over. So streaming multiprocessor version and everything is defined by this compute capability. Determine the hardware features and the available instruction, comprise of major, minor revision. The core architecture is the minor version. Specify the incremental improvements over the core architecture. So these are like very old ones. That's why I'm having the compute capabilities right now in here. So so in here, what we see is the implementation capabilities. So depending on your hardware, depending on what it can do, the compute capability changes. So the compute capability available on these architectures. The Tesla architecture is 1.0 and Turing architecture it's around 7.5. So these compute capabilities changed on the different hardware, the CUDA level, and everything that you will see within the applications. Okay, so just remember the compute capabilities. We will look into this. So we know what is host, we know what is the device is, what is a stream multiprocessor and all. So next thing that we need to know, at least in this context, is the kernel. So this is the one that is most important in terms of CUDA programming executions. Okay, so the first thing that we need to make sure that this is the kernel. Kernel is the kernel is the function that launches and executed programs. Okay, so the kernel is a function that is running within the GPU itself. Okay, remember kernel function have a few what do you call few characteristics. Okay, the kernel function is a void function. That means a kernel function do not have a return thing. Okay, and usually the host and executed asynchronously. Sorry. So the kernel function that is launched usually by the host and executed asynchronously. So when we are talking about kernel function, it is executed on the host. So remember, the host is CPU and the kernel functions are executed in the host in asynchronous way. Okay, and the function is executed usually by the host and executed asynchrony on the device. So initiation happens in host. Okay, but the function get executed, the results, the things that we need to work is going to be happening on the device itself. Okay, so you guys can see launch from the host by @kernel method, and execution happens in the device itself. So the kernel functions, remember these things launch, or these things start from the what do you call the host machine, but executions, whenever the executions happen in the device itself. Okay, we'll see some kernel functions and everything later on. And the kernel code, the kernel thread has built-in variables. Okay, every kernel function have some built-in variable. So the first one is block dim, and the second one is block IDX, and the thread IDX. Okay, so just remember these are there. We will get a full introduction how these things are accessed, but for now remember a kernel function has built-in variables. Any kernel functions that we run has these three variables built onto it. Okay, the first one is block dim, block dimension, block IDX, and thread IDX. we'll see what is these things in much more broader. Right now, remember these things are there. And there is something called device function. Okay, we have the kernel function, functions that run on the device. Okay, so these functions have a different purpose than the kernel functions. So the differentiation happens. It's going to be defined by __ device. A kernel will be specified by __ global. So that is how we know, okay, this one is a kernel function. This one is a device function. Okay. So what do you understand by a device function? What do you understand by a global function or a kernel function? So the main purpose of the device function is that can be called from a kernel or another device function. That means when we are defining a device function, the device function can be only called from the kernel function itself. The kernel function, something like this, something start with __ global __ or another device function. Okay, only within those two places that we can call a device function. Otherwise, the device function would not work. Okay, these device functions cannot be called from the host. That means if you are trying to execute these device functions within your host, that means from your CPU, this simply does not work. Okay. And one important characteristic here is that device function can return a value. Okay, it can return a value. So we will see these things in action, why these things are defined in this way, why global functions or the kernel functions are void, why device functions are not void, why device functions can be only called within the application or within the device itself. Okay, so we will look into these things in upcoming lectures. For now, have these terminologies remembered, because we're gonna often use these things. What is a host? What is the device? What is SM? What is compute capability? What is defined? What is known by kernel? What is known by device functions? So you guys need to know where the context is, what is the use case, at least what is the definition by it right now, and what are these variables. We will move on to these things in upcoming lectures, and probably this diagram is the will explain all the kernel functions and device functions that you need to know. So we have a good practice or good knowledge on each and every one of these things. Okay. All right. So that's for today. Any questions within these things? Okay. Let me stop sharing. Okay. Let me stop recording.